Welcome. Welcome to Sweet Speak. Today we're joined by Daryle Serrant. Daryle's a leading voice in AI innovation and currently a research scientist at Kauai, a nonprofit that I also serve on as an advisory function. At Kauai, he's helping shape the future of decentralized, efficient AI. So Daryl's the founder and CEO of Byte Solid Solutions. His background includes impactful roles at Tesla, Lockheed Martin, multiple startups, where he applied machine learning to solve complex challenges in aerospace and in energy and beyond. He's also a passionate educator, known for making advanced AI concepts accessible through his courses and mentorship. So, in this episode of Sweet Speak, we're going to dive into state space models, a powerful alternative to transformers, and explore how they're enabling dynamic memory and faster, scalable AI. So, Daryle's going to unpack why SSMs matter for agentic AI and where this emerging architecture is headed. Daryl, thank you so much for joining us today.
Yeah, thank you for inviting me to talk.
So this is going to be fun. But first, for those who aren't aware, let's start with what is state space model and how does that differ fundamentally from the transformer architecture?
Yes, so state space models is not a entirely new concept. It's actually been something that's been around for decades, used primarily in like the engineering, economic space, where the goal is, let's say, for example, you want to try to model that dynamics in a system. Let's say, how um, let's say you have engineering systems, like a complex system, like a I'm trying to figure a good one, like a missile or like some target you're trying to track over time. Um, Varies as you combine different signals, like say temperature, um, some other different measurements, like sensor fusion.
Mhm.
State space models has been a kind of a classic method that's been used to kind of track how these complex systems evolve over time by track through like different variables, fixed variables. So the idea here is a lot of the modern AI systems that we're looking at right now, like Chat GPT, all these AI applications, they are powered using a neural network architecture called the transformer. And
Mhm.
one of the problems with transformers is that as your input, the size of the text or the data you put into the models, it grows, the amount of computation, the amount of memory you need scales over time. So that becomes really problematic when, let's say, you're trying to do analysis on, let's say, very long documents or long sequences of data. So state space models has been as a potential as a solution that's been explored to kind of address that, where now you're using, instead of using attention to kind of try to calculate relationships between different sequences and try to, let's say, predict the next word, you're using state space models to try to track those those relationships between the data over time, the sequences, the dependencies, and that allows an AI model to actually perform computations much faster, more linearly than what a transformer would accomplish. And I can give you another way to kind of understand that, like more of an analogy that help you kind of figure out what it means. So pretend, for example, let's say, for example, you are I'm glad I finally have a chance to actually use this analogy because it's been in my head for a while. So let's
Bring it.
say, for example, you're on a road trip and you're driving, and your goal is to try to figure out where do you want to go next. So let's say, imagine, okay, so every second you stop, and then you pull out your trip planner, your long uh, map, and you try to figure, okay, where did I go before? Like, okay, where did I start? What are all the different turns that I made on the journey? And then you look at all this, and then you try to figure out where to go next. So that's essentially how transformers work. They every new word they try to predict, they stop and look at all the data, all the words that they've looked at that they've analyzed before, and try to predict the next word. So as you can imagine, that's very computationally expensive. Um, what state space models do is they try to do this over time. So as you're driving, you keep a, let's say, like a little dashboard or a mental map memory model of all the different decisions that you've made over time. So that way you're not you're actually as you're driving, you're keeping like a little mental model, like a little dashboard that you look at and you glance at it. It's like, okay, now I want to go this place next. I want to stop for coffee. I want to go talk to my friend. So it's much more efficient, and it's really useful for cases where you are trying to process long amount of data, like documents or signals, or you're trying to reason over long sequences. Um,
Yeah, I want to take that because this is like you mentioned, it's been around a bit. But what inspired your interest in state space models, and what drew you to explore their potential over the more widely used models that many of us are familiar with today?
yeah. So one of the things that really drove me to state space models is my background is I've worked as a software engineer. I've worked on embedded systems, and I actually still do for some of my clients. Uh, and what I was really interested in is trying to combine, my background in embedded software, my experience being a data scientist and machine learning engineer, and what really what I thought was really interesting is trying to develop systems, AI models, or systems that can go drive on the edge computing. So that's when state space models was kind of drew my attention. Where if you could actually build models or AI models that are smaller and compact, that can actually be run on the edge devices, this could change the game for a lot of companies that are trying to build more of these intelligent systems that's more more accessible to the public. So you imagine, for example, you have uh, uh, a model that can be put on your phone that can be used for cases where you're more concerned about, let's say, security, making sure that your users are able to use AI without having to worry about it being transmitted to a third party server, or cases where you want to build an AI model that's you want to build an apps that provide a more immersive, more responsive experience to your users. But one of the biggest challenges is these large, huge, complex models. They can't sit on your phone. You have to put it on the cloud, and even if you're able to put a model on the phone, it could take so much computational power that it's not even worth it. So I saw state space models as one potential piece that solves that puzzle. Where if you can get an AI model that's smaller, more compact enough, that you can use it to build great, powerfully interesting applications, and that serves a lot of these purposes, especially in industries like healthcare, or let's say defense. Defense is a big one, and yeah, and autonomous self-driving, robotics too. Yeah.
Yeah, let's dive into that a little bit more, Daryle, because one of the key benefits of SSMs is their ability to build dynamic internal memory. Talk to me, how does that actually work in practice?
Yes. So in practice, so if you imagine, one of the things I mentioned about attention mechanism in transformers is that it's calculating. So as it's processing data, it's calculating the relationships between each token in an input sequence. It's every other token. What a state space model, or more appropriately, more than state space based neural networks like Mamba do, is they are essentially compressing. If you imagine that they're compressing this entire signal data into some sort of compressed representation, where it's not capturing, remembering every piece of information. It's trying to figure out the most important points in the input to remember, to compress. So what that does, it allows you to make uh, reason over these long sequences of data without the computation and memory costs.
Yeah. So I guess what ways do
What
SSMs
ways?
manage information over
Yeah.
time more efficiently than those attention-based models.
Yes. So it's so think about it as so I mentioned the compression. That's one part of it, but there's also a component in these state space models where it's picking the most important um, signals in the data over time as it's looking through the data. It's picking the most important pieces of information that it needs to remember in order to, let's say, successfully model the dynamics in a input data in a sequence. So for tasks, let's say like trying to uh, let's say you have a time series task where, for example, let's say you have an application where you have a long continuous signal in real time, and your goal is to try based on what everything that's happened so far, all the signal data you had so from the beginning of time, try to figure out, okay, what's is there an anomaly, or try to predict some sort of action to do. One of the biggest problems with like using a transformer to do it is that you're limited in context. You have a fixed context window. Um, but with state space model, because the idea is you're not holding on to everything. You're trying to basically create some sort of compression. Think about it like an image. So you're when you compress an image, you're figuring out the most important details in that image that you need. State space models is kind of the same thing here, where you're figuring out you have some sort of and the way they do it is you have a structure, like a state matrix that you use to kind of capture the most important uh, information globally in your signal, and that allows you to make more accurate predictions about about the data, like what happens next, without the loss, all the computation and memory cost that a transformer typically would have.
So talk to me about the scalability then of
Yeah,
SSM, especially in real time or resource constrained environments.
yeah. So for a model like transformer based attention based models, the computation scales quadratically, because again, you're doing that. You're every time you're trying to make a prediction of a next token, you're having to recalculate relationships between each input sequence. So that's quadratic. For state space models, because you're doing this kind of it's more of a linear um, scaling. So as you put more as the link input size increases, the computation for those models it scales linearly instead of quadratically like transformers.
Let's talk agentic, right?
Agentic.
Because right now, agentic is everything everybody's saying. Listen, a year ago, everybody's talking Gen AI. Now it's agentic AI, and there's so many other versions of AI we're going to be talking about. It's got the spotlight right now. But how do you think SSMs are particularly well suited for that agentic AI, those autonomous systems that perceive, reason, and act over time?
Yeah. So one of the biggest problems with so agentic AI is all about trying to based on some input. Like you're taking you have an autonomous system that tries to determine, okay, I take some action. I'm given some instruction to do. I take some action, and I have to look at all the actions that I've done before in the past to kind of figure out what to do next. One of the challenges with kind of the more of today's agents is that um, as the history of these actions grow, you have the problem with trying to kind of keep accurate recollection of all the actions that's done before in order to make a decision or figure out what to do next. What state space models provide for agents is an opportunity to kind of create more of a compressed history of everything that's been done before. So not only you can actually take these actions much sooner, but you don't have the kind of memory restrictions that a lot of the transformer-based models have today, where there's only a certain context that you can remember, um, and afterwards the results that you get from these agents kind of decline. State space models provide a way to kind of keep a gist. So it's almost like, for example, let's say you're having a conversation. I'll give you an example. Let's say you're having a conversation with yeah, this is like a chat bot where you're trying to have a conversation with a customer, and um, as the conversation, as the length of the conversation grows, it gets really, really long. There's only so much that a chatbot can remember. What a state space model allows you to do is it allows you to kind of keep a compressed, try to remember kind of the gist of it, where almost like you're talking to a human, where you don't, when you're in a conversation, you kind of remember, you figure out what's the most important information to keep to remember right now, and you kind of compress what's the points in the conversation that happened earlier. So that's essentially what a state space model provides, and this allows agents to kind of be more intelligent of what information it remembers, like more of the recent information that it remembers, and what some of the more information that happened more in the past that it should kind of summarize or keep it compressed. If that makes sense, if that's clear.
And so to dive into that a little bit further, the state space model, how does it change how AI agents plan, reflect, or reason? Memory retention's one, compression's another, but especially compared to today's generative models, how is it going to fundamentally change AI agents?
Yeah, so I think it's going to allow to build more agents that can actually respond faster in real time, because you have that again, that where it really shines is the ability to look at a lot of data, long sequences of data, and reason in a faster, more dynamic way. So I think that's what I see it's really shining. Um,
So I have to ask this,
yeah.
Daryle, then, because we have all these wonderful. It's going to make the world great. It's going to be make things quicker and better memory retention. Where do SSMs fall short?
Yeah, so obviously SSMs are not they're still early in development, and there's a lot of research in trying to figure out how to make it better. Where one element where it falls particularly really short is in terms of situations where, because again, with state space models like Mamba, you're essentially doing a compression of information. So think about it as like a lossy compression, like if images. So it's not going to remember exactly all the details of the information that's being compressed. So in situations like where you need more of fine-grained recall of specific details in your documents, it's not going to do as well as a transformer-based model. So what I see a lot of research and more the practical applications I've seen through my research and also industries is that they build neural network architectures that combine make that mix transformer attention based mechanisms with the Mamba blocks, and allows them to create models that have kind of like the combination, the best of both worlds, the um, the accuracy and recalling like minute details, but also the fast processing of long sequences of data. And I can give you examples of models that are where they've done that. Like Jamba is one good example of that. Um, that's been developed by, I think it's AI 21, and I'm probably not saying that right. IBM actually they built an SSM called Bamba, the BAMBA, where it's basically like a 9 billion parameter model that combines like detention blocks with Mamba blocks, and allows them to get like twice as fast as process a long sequences of data, like the documents, twice as fast as transformers with similar accuracy. And then also NVIDIA, they also released another model called like HIMBA, HIMBA. It's just where they're using it uh, for more, another one that's has a more high performance uh, model of mixture of transformers with Mamba blocks. Adobe also has a similar model where they're using it for actually image generation. That's what I think is pretty image and video generation, which is, sounds really pretty amazing. So actually, there's a lot of companies that are using it today. Like a lot of big name companies that are using these state-space models for some of their work today. And what I anticipate is as more of these models, companies release some more of these models on like sites like Hugging Face or on their own sites, you'll see a lot more of these startups start using it in some of their products as well.
Yeah, let's dive a little more into that too,
Yeah,
because you mentioned IBM, Adobe, NVIDIA, many
yeah,
others are doing these early deployments of using SSMs. What are you seeing that hint at the future potential for SSMs?
yeah. I see it as it's going to be a great technology to use as we start getting more people start getting more and more data or understanding of what some of the benefits and limitations of it. I can see it's just particularly definitely being used for more of these kind of, again, like these real-time applications um, where kind of fast, like real-time responsiveness is important. Um, but I also see that, a lot of the technology right now is based is more transformer based. So we have a lot of companies that have a lot of companies that invested a lot of money, millions of dollars in building these systems, tooling around attention or transformer based. So I would assume that it's going to take some time, a couple years before you start seeing uh, a lot of infrastructure built around kind of state-space models. But I do see in the near future, maybe the next 3 or 4 years, more and more companies releasing models or AI models that use some of use state-space models. Not probably not basically casting out transformers entirely, but start mixing it into their architectures.
Well, I guess that, with all the buzz around AI in every single industry, do you think people are ready to embrace a shift towards architectures like SSMs? And are we still really early
It's it's
experimentation?
it's still really early in experimentation. Yeah. But I
Yeah.
I would see it'll start becoming more and more mainstream over time as they start more people starts playing with it, more people seeing the benefits, and more research is done to kind of improve some of the limitation, the downsides of it.
All this is moving so quickly,
Yeah.
right? And we wouldn't even be having this conversation a year ago, right? So as we look and fast forward, let's. I always love to say, what's 3 years in advance? It's going to be so different. Talk to me about a year from now, 18 months from now. What role do you see SSMs playing in the evolution of AI systems?
Yeah. I see it playing more of a um, especially for more like these more talking about these more kind of on device systems where you're trying to build AI models that are more accessible to the general public. Um, I can see it playing a really big role in those kind of um, developing those technologies, and in particular with some of the work that's being done with Quai, where they're trying to build more democratized AI that anyone can actually use who may not have the resources that a company like Google or Amazon have, and they want to be able to use AI in their own on their own personal computers, but they can't. So I see these small language models like and particularly state-space models playing a role in making that happen. Uh,
What excites you most about this?
Yeah, I think what really excites me the most is, kind of combining some of my backgrounds, like because I'm always looking for ways to kind of take what I've done in the past and kind of combine it in the new and creative way. So what I was really excites me the most is really being able to build these smart, intelligent systems that work on more smaller resource constrained environments where you have like a power an energy constraint or you have a memory constraint. So I'm really excited to see how as more research is being done on this technology, what can be done to make AI more accessible to in places that normally wouldn't.
This has been fantastic. Before I let you go, talk to me about Bite Solid Solutions. What do you all do there?
Yeah, so Bite Solid Solutions, I like to say I have a slogan. I help companies make go from bewildered to brilliant. So I provide a lot of education in terms of helping uh, owners of small businesses really understand AI, how could they apply it in their business, and I kind of guide them through the process of um, the type of different types of models they should consider to use, how they actually could get their data or their tooling right to kind of take advantage of AI. And I also help startups in terms of software development, helping them to build some of their early proof of concepts that they need to get your building went for ready to pitch to investors. And then I also provide, education. I publish courses on different platforms like Pluralsight that really educates and empowers developers on how to use AI and these technologies. So yeah, it's really been a really exciting time. I started it around in 2020 during COVID, so it's really been exciting to see all the kinds of things I've been able to do and the people I've been able to help with the work that I do.
Wonderful. Daryle, thank you so much for shedding light on state space models and where things are going. Again, let's put it in our calendar, right? Let's sit here in another 18 months and look at this and see how much is different, how much has changed, what organizations have truly embraced and adopted as the evolution of AI continues. Daryle, thank you so much for joining us today.
Yeah, thank you.